Welcome to Lesson 4.3, Configuring Training Parameters. Overview. Training parameters can make or break your fine-tuning results. Too high learning rate? Model diverges. Too small batch size? Training takes forever. In this lesson, you'll learn to configure training parameters optimally for your Tesla P40 GPUs. Duration: 45 minutes. Difficulty: intermediate. Learning objectives. By the end of this lesson, you will understand key training hyperparameters, choose optimal learning rates, configure batch sizes for Tesla P40, set up gradient accumulation, configure warm-up and learning rate scheduling, enable memory-efficient training on Windows, set up logging and checkpointing. Key training parameters. 1. Learning rate. How big each update step is. 2. Batch size. How many examples per update? 3. Epochs. How many times to see full dataset? 4. Warm-up. Gradual learning rate increase at start. 5. Scheduler. Learning rate changes during training. Learning rate. Learning rate equals step size for updating model weights. Too high. Model diverges. Loss goes to infinity. Too low. Training too slow. Might get stuck. Just right. Steady loss decrease. Model size, learning rate, notes. 1 to 3B params, 2E4 to 5E4. Higher is fine for small models. 7 to 13B params, 1E4 to 2E4. Standard range. 30B plus params, 5E5 to 1E4. Lower for large models. For Llama 3.23b with LoRa, start with 2E4. Scheduler equals changes learning rate during training. Common schedules. 1. Constant, same LR throughout. Python, LR scheduler, type, constant. 2. Linear, gradually decrease to 0. Python, LR scheduler, type, linear. 3. Cosine, smooth decrease curve recommended. Python, LR scheduler, type, cosine. For this module, use cosine. Batch size. Per device batch size equals examples processed per GPU step. Effective batch size equals per device batch size x num GPUs x gradient accumulation steps. For Llama 3.23b, 4-bit, average 200 tokens example. Config, VRAM usage, speed, recommended. Batch 1, grad AC 1. HR8 GB, slow, too slow. Batch 2, grad AX 4. 10 GB, good, safe start. Batch 4, grad AC 2. 12 GB, better, good balance. Batch 8, grad AC 1. 16 GB, best, may, on long sequences. Start with Batch 4, Gradient Accumulation 2, Effective Batch IL8. Why use it? Simulates larger batch size without memory cost. Accumulate gradients over n steps, then update weights. In this code snippet, we're configuring the training parameters for our model. The per-device train batch size is set to 2. Which indicates the number of samples processed on each device during a single forward and backward pass. This is crucial because it ensures that the batch fits within the available VRAM of your GPU. Next, we have gradient accumulation steps set to 4. This means that instead of updating the model weights after every batch, we will accumulate gradients over 4 batches before performing an update. This effectively increases our batch size to 8. Calculated by multiplying the 2 parameters. This approach allows us to simulate a larger batch size without needing additional memory, which can lead to better training stability and performance. Rules. Effective batch size 832 is good for most tasks. Larger batch equals more stable, but risk of overfitting on small datasets. Smaller batch equals more noise, often generalizes better. Epochs and steps. Epoch equals 1 complete pass through entire dataset. Example: 100 training examples. Batch size: 4. 1 epoch equal 100. 4 equals 25 steps. Chap dataset size, recommended epochs. Notes. 10 to 50 examples. 10 to 20. Small data, need multiple passes. 50 to 200 examples. 3 to 5. Standard range. 200 to 1,000 examples. 2 to 3. Larger data. 1,000 plus examples. 1 to 2. Large data, risk overfitting. For 100 to 200 examples, use 3 epochs. Setting the num-train epochs to 3 means that the model will go through the entire training dataset 3 times. This is an essential parameter because it determines how many times the learning algorithm will adjust the model weights based on the training data. Training for multiple epochs allows the model to learn more complex patterns and improve its performance, but it's important to balance this with the risk of overfitting. In this case, 3 epochs is often a good starting point, especially if you're working with a smaller data set. Adjusting this number can help you find the sweet spot for your specific task, so keep an eye on your model's performance as you experiment. This code sets the training parameter, max steps, to 300, which means the model will train for a fixed number of 300 steps. It's important to note that this parameter overrides the num-train epochs setting, allowing you to control the training duration more precisely. Specifying max steps is particularly useful when you want to ensure that training doesn't exceed a certain limit, which can help manage training time and resource usage effectively. By controlling the number of steps, you can experiment with different configurations without needing to adjust epoch counts, making it easier to find the optimal training duration for your specific dataset and model. For this module, use num-train epochs 3. Warm-up. Warm-up equals gradually increase learning rate from 0 to target. Why? Prevents early instability. Helps model adjust to new task. Standard practice in fine-tuning. Warm-up steps equals number of steps to reach full learning rate. Rules of thumb. Short training, 500 steps, 5 to 10% of steps. Medium training, 500 to 2,000 steps, 10 to 20 steps. Long training, 2,000 steps, 100 to 500 steps. Example. In this code snippet, we're setting up key training parameters for our model fine-tuning process. The variable num-train epochs is defined as 3, meaning the model will go through the entire dataset 3 times. This is essential for allowing the model to learn from the data effectively. Next, we calculate the total training steps based on the dataset size and batch size. For instance, with 120 examples and a batch size of 4, we determine that we will have approximately 90 steps in total. This calculation ensures that we know how many iterations the model will perform during training. Finally, we set warm-up steps to 10, which is about 11% of our total steps. This warm-up phase is crucial as it helps stabilize the training process by gradually increasing the learning rate, preventing potential issues that can arise from starting too aggressively. For 100-300 total steps, use warm-up steps 10. Complete training configuration. This code snippet sets up the training parameters for fine-tuning a language model using the Transformers library and unsloth. The training arguments class is essential as it defines how the training process will be conducted. You'll notice the output dir specifies where to save model checkpoints, ensuring you can resume training or evaluate later. The num-train epochs is set to 3, meaning the model will see the entire dataset 3 times, which is crucial for learning. Batch sizes are defined for training and evaluation, and gradient accumulation is used to effectively increase the batch size without requiring more memory. The learning rate and its scheduling are configured to help the model converge smoothly. Memory-efficient optimizers like AtomDO 8-bit are specified to optimize performance, and precision settings adjust for hardware capabilities. Logging and evaluation strategies are included to monitor progress, while checkpointing ensures you don't lose your work. Finally, a reproducibility seed is set, and the output confirms that the training configuration was successfully created. This structured setup is vital for effective model training. Optimizer choice. This line of code sets the optimization algorithm to AtomW 8-bit. Using AtomW with 8-bit precision is essential for fine-tuning large language models efficiently, as it reduces memory usage while maintaining performance. This is particularly beneficial when working with limited resources or larger datasets. By specifying this optimization method, you're instructing the training process to leverage the advantages of 8-bit computation, which can lead to faster training times and lower memory consumption. It's a practical choice that balances performance with resource constraints, ensuring that your model can learn effectively without overwhelming your system. Benefits: 75% less memory than regular AtomW. Minimal quality loss. Works great on Windows. Perfect for Tesla P40. Hit Optimizer. Memory, speed, quality, Windows. Atom 8-bit. Low. Fast. Excellent. Best. Atom Torch. High. Fast. Excellent. Works. SGD. Very low. Fast. Good. Works. Add a factor. Low. Slow. Good. Works. For this module, use AtomW 8-bit. Monitoring and logging. This line of code sets the logging frequency during training to every 10 steps. By adjusting the logging steps parameter, you ensure that the training process provides updates at regular intervals, which can be crucial for monitoring the model's performance and diagnosing any issues that may arise. Logging every 10 steps allows you to track metrics like loss and accuracy without overwhelming your output with too much information. This balance is especially important when working with large datasets or lengthy training sessions, as it helps you stay informed about the training progress while keeping the logs manageable. What gets logged? Training loss, learning rate, gradient norm, steps per second. This code snippet configures the evaluation strategy for your model training. Setting eval strategy to steps means that the model will be evaluated at regular intervals during training rather than just at the end. This is important because it allows you to monitor the model's performance and make adjustments if necessary, ensuring that it is learning effectively. The eval steps parameter specifies that the evaluation will occur every 25 training steps. This frequency strikes a balance between getting timely feedback on the model's progress and not overwhelming the system with too many evaluations. By keeping an eye on the evaluation metrics, you can catch potential issues early and optimize your training process. What gets evaluated? Validation loss. Perplexity, optional. Why evaluate during training? Detect overfitting early. Choose best checkpoint. Stop training if validation loss increases. Checkpointing strategy. This code snippet configures the training parameters for saving checkpoints during the fine-tuning process. The save strategy is set to steps, which means that the model will save its state at regular intervals rather than at the end of the entire training. Specifically, save steps is defined as 50, indicating that a checkpoint will be created every 50 training steps. This is crucial for preventing data loss in case of interruptions and allows you to resume training from the last saved state. The save total limit is set to 3, which ensures that only the last 3 checkpoints are retained. This helps manage disk space by automatically deleting older checkpoints beyond this limit. Overall, these settings provide a balance between safety and resource management during training. Checkpoint includes model weights, LoRa adapters, optimizer state, training state, random seed state, storage, LoRa checkpoint, 50,100 MB, full trainer state, 200,500 MB. For 100-step training, saves at steps 50, 100. This code snippet is setting up the SFT trainer to resume training from a specific checkpoint. In this case, outputs checkpoint 50. Resuming from a checkpoint is crucial when you want to continue training a model without starting from scratch, especially if the previous training was interrupted or if you want to fine-tune further on an already established model. The training args variable contains all your training parameters, such as learning rate, batch size, and number of epochs. By specifying the checkpoint, the trainer will load the model weights and optimizer state from that point, allowing for a seamless continuation of the training process. Once you run this, you'll see output confirming that the training has resumed, along with logs indicating the current epoch and loss values, which helps you monitor the model's performance as it continues to learn. Configuration presets. This code snippet sets up the training parameters for fine-tuning your language model using the training arguments class. The output dir specifies where your model outputs will be saved, which is crucial for organizing your results. The max steps is set to 50, indicating a very short training duration, suitable for quick tests or debugging. The per-device train batch size of 4 defines how many samples will be processed at once on each device, balancing memory usage and training speed. The learning rate of 2E4 is a standard starting point for many models, while warm-up steps at 5 helps stabilize training initially. Logging every 10 steps allows you to monitor progress without overwhelming your output. Both eval strategy and save strategy are set to no, meaning no evaluation or checkpoints will be created during this run. Finally, using AtomW 8-bit optimizes memory usage, and enabling FP16 allows for faster training with reduced precision. This configuration is tailored for quick experimentation, ensuring you can iterate efficiently. Use for testing pipeline debugging. This code sets up the training parameters for fine-tuning your model with unsloth. The output dir specifies where to save the model outputs, which is essential for tracking your progress and results. The numtrain epochs is set to 3, meaning the model will go through the entire training dataset 3 times, which helps improve its performance. The per-device train batch size of 4 indicates how many samples will be processed at once, while gradient accumulation steps of 2 allows you to effectively double your batch size without increasing memory usage. The learning rate is set to 2E4, which controls how quickly the model learns, and using a cosine learning rate scheduler helps adjust this rate over time for better convergence. The warm-up steps and logging steps parameters help manage the training process by gradually increasing the learning rate initially and logging progress every 10 steps. The evaluation strategy is set to check performance every 25 steps, and the model will save its state every 50 steps, with a limit of 3 saved models to manage storage efficiently. Using AtomW 8-bit for optimization reduces memory usage, while enabling FP16 allows for faster computations with half-precision floating points. Finally, gradient checkpointing helps save memory during training by storing only a subset of intermediate results. Overall, these configurations are crucial for optimizing your training process and ensuring efficient resource use. Use for most fine-tuning projects. This code snippet sets up the training parameters for fine-tuning your language model using the training arguments class. Each parameter plays a crucial role in how the model learns and performs. The output dir specifies where to save the model checkpoints. The numtrain epochs is set to 5, allowing the model to learn from the data over multiple passes. A smaller per-device train batch size of 2 means more frequent updates, which can improve convergence. The gradient accumulation steps of 4 helps simulate a larger batch size without requiring more memory. The learning rate is lowered to 1E-4, which is often necessary for fine-tuning to prevent overshooting optimal weights. The LR scheduler type is set to cosine, which adjusts the learning rate dynamically, while warm-up steps helps stabilize training at the start. Logging and evaluation strategies are configured to provide insights during training, with checkpoints saved every 25 steps and limited to 5 total. Using Atom 8-bit optimizes memory usage, and enabling FP16 allows for faster computations. The gradient checkpointing option saves memory by trading off some computation, while weight decay and max grad norm help prevent overfitting. Overall, these settings are designed to balance training efficiency and model performance. Use for production models, critical applications. Windows-specific settings. This code snippet configures essential training parameters for fine-tuning your model with unsloth on Windows. First, it sets the optimizer to AtomW 8-bit, which is efficient for memory usage and helps speed up training without sacrificing performance. Next, it specifies the use of FP16, or half-precision floating point, which is particularly beneficial on the Tesla P40, allowing for faster computations while still maintaining model accuracy. Note that BF16 is set to false here, as it isn't supported on this setup. Enabling gradient checkpointing is also crucial. It saves memory by storing only a subset of intermediate activations during the forward pass, which can significantly reduce memory usage during training. The comment about flash attention highlights that it's not available on Windows, so we won't be using it here. Lastly, the data loader workers are set to 0, or a maximum of 1 or 2, which is a practical choice on Windows to prevent potential performance issues. Adjusting these parameters ensures a smoother training process tailored to your environment. Unsloth automatically handles most Windows quirks. Testing configuration. This code snippet is designed to test and confirm the training configuration before you start the actual training process. It prints out key parameters that will guide the training, such as the total number of training examples and the batch size. The effective batch size, which is the product of the per-device batch size and the gradient accumulation steps, is also calculated here. You'll notice the calculation for steps per epoch and total training steps, which are crucial for understanding how long your training will run. The output will show you how many steps you'll evaluate and how often checkpoints will be saved. This information helps ensure that your training setup aligns with your expectations and allows you to make any necessary adjustments before proceeding. Configuration checklist. This checklist is essential for ensuring that your training parameters are well configured before you start fine-tuning your model. Each section addresses a critical aspect of the training process. For the learning rate, you want to select a value appropriate for your model size, like 2E4 for a 3 billion parameter model. The scheduler and warm-up steps help stabilize training early on. In the batch size section, ensure that your physical batch size fits within your GPU's VRAM, and consider using gradient accumulation to effectively increase your batch size without exceeding memory limits. When it comes to training length, setting the right number of epochs and calculating total steps helps avoid overfitting while still allowing your model to learn effectively. Memory optimizations like enabling an 8-bit optimizer and FP16 can significantly improve performance on compatible GPUs. Finally, logging and checkpointing are crucial for tracking progress and saving your model at intervals. Once all items are checked, you can confidently proceed with training. Hands-on exercise. This code snippet is focused on configuring the training parameters for your model. First, it reminds you to input the statistics from your dataset, including the number of training examples, average token length, and maximum token length. These metrics are crucial as they directly influence how your model learns. Next, you'll calculate several important values: the steps per epoch based on a batch size of 4, the total steps for your training duration of 3 epochs, and the warm-up steps, which are set to 10% of the total steps. Additionally, you'll determine evaluation steps, which occur every 25 to 30% of an epoch, and save steps for checkpoints at the midpoint and end of training. Finally, you'll create a training arguments object using these calculated values. This configuration is essential as it defines how your model will train, ensuring efficient learning and performance monitoring throughout the process. Key takeaways. 1. Learning rate. 2E4. Good starting point for LoRa on 3B models. 2. Batch size 4. Grad ACC 2. Safe for Tesla P40. 3. 3 epochs. Standard for 100-200 examples. 4. Cosine scheduler. Smooth LR decrease. 5. Warm-up 10 steps. Stabilize early training. 6. AtomW 8-bit. Memory efficient on Windows. 7. Evaluate during training. Catch overfitting early. What's next? Configuration set. Time to actually train your model. Continue to Lesson 4.4, Training Your First Model. Additional resources. Hugging face training arguments. Learning rate schedules. Gradient accumulation explained. Adam W. Paper. Lesson complete. This image illustrates different learning rate schedules in a comparison chart. Here, we see three distinct approaches to manage the learning rate during training: cosine decay, linear decay, and a constant learning rate. The green line represents cosine decay, which is recommended for its effective balance in adjusting the learning rate over time. You'll notice it starts high, allowing for rapid learning, and then gradually decreases, helping to refine the model. The blue line denotes linear decay, which decreases the learning rate linearly as training progresses, and the orange dashed line represents a constant learning rate that remains unchanged during training, which might not be as effective for many situations. Understanding these schedules is crucial because they influence how quickly your model can converge on patterns in the data and avoid issues like overshooting the optimal solution. For your next steps, consider experimenting with these different learning rate schedules in your own fine-tuning process, starting with the cosine decay as it often yields the best results. This image illustrates the effect of low-rank adaptation, or LoRa rank, on training loss as the training progresses. Each line represents a different rank value, with the varying colors indicating ranks of 4, 8, 16, 32, and 64. You can see that as training progresses, the loss decreases for all ranks, but they do so at different rates. The rank value significantly influences how quickly and effectively the model converges. For instance, the lines for ranks 4 and 8 show a much more rapid decline in loss early on compared to higher ranks, particularly rank 64, which improves more slowly. This indicates that lower ranks might allow for faster training convergence, while higher ranks may offer slower improvements, possibly due to a more complex model learning larger parameter adjustments. Understanding these dynamics is critical because it helps you determine the optimal rank for your own training scenarios. As you proceed with your fine-tuning, experiment with different rank values within your own models to see how they affect training loss and convergence speed. This is a great way to refine your approach and enhance your model's performance. This image explains gradient accumulation, specifically how to simulate large batch sizes while working with limited video RAM. Here, you see a simulated batch size of 16 that is achieved by breaking it down into smaller micro batches of 4, as indicated by the gradient accumulation steps set to 4. In this setup, we accumulate gradients over those 4 micro batches before performing an optimizer step. This pattern allows us to effectively manage memory usage while still leveraging the benefits of larger batch sizes. You begin by processing the first 4 samples to gather their gradients, then move to the next 4, accumulating each time until you've processed all 16 samples. Once you've accumulated gradients over the 4 micro batches, you execute the optimizer step, which updates the weights only after processing all 16 samples. This method is crucial when you're facing VRAM constraints, as it allows you to keep training performance high without overwhelming your hardware. As you move forward, try to implement this strategy in your own training loop and monitor how it affects performance and memory requirements. This approach will become a valuable tool in your fine-tuning workflow. This image shows a heat map illustrating the hyperparameter sensitivity, specifically focusing on the final training loss for various combinations of batch sizes and learning rates. Each cell in this grid represents the loss value achieved with a particular pairing of these two hyperparameters. The left side of the chart details the learning rates, ranging from 5E5 to 3E3, while the bottom axis lists the batch sizes from 4 to 32. As you observe the values, the lower the loss, the better the model's performance. You can see that the combinations yielding the lowest loss values, like 0.52 and 0.55, are associated with smaller batch sizes and moderate learning rates. Understanding this heat map is crucial as it helps you identify the most effective hyperparameter combinations for fine-tuning your model. By selecting these optimal values, you'll increase the likelihood of achieving better performance in your training. The next step is to experiment with the hyperparameter combinations that have shown the most promise here, and apply them to train your first model using the Unsloth library. This image illustrates the warm-up learning rate schedules used during training. You're seeing two key methods here. The blue line represents a linear warm-up with a constant learning rate, while the green line shows a linear warm-up followed by a cosine decay. The purpose of the warm-up phase is to gradually increase the learning rate from 0 to its initial value, preventing large weight updates in the early stages of training. You'll notice that the blue line levels off after the initial ramp-up, maintaining a constant learning rate. In contrast, the green line shows how the learning rate decreases after reaching its peak, which helps fine-tune the model as training progresses. The dashed orange line indicates the endpoint of the warm-up period, set at step 30 in this scenario. Understanding these schedules is crucial because they impact how effectively your model learns. For your next steps, consider experimenting with these different warm-up strategies in your training process. Tuning the learning rate can significantly affect your results, so it's worth testing to find what works best for your specific model and dataset. This image displays two graphs comparing LoRa rank to both quality and the number of trainable parameters. On the left, we see the relationship between LoRa rank and relative quality percentage. As the rank increases from 4 to 128, the quality improves significantly, leveling off around 100%. This indicates that using a higher rank can enhance the performance of your model, but after reaching a certain point, the quality gains diminish. On the right, we have the graph illustrating LoRa rank against the count of trainable parameters. Here, you can observe a more gradual increase in parameters as the rank rises, particularly experiencing a spike at rank 32. This suggests that while a higher rank may improve quality, it also increases the complexity of your model through a greater number of trainable parameters. Understanding this balance is crucial. You want to find an optimal rank that gives you the best quality while managing the number of parameters for efficiency. As you proceed, consider experimenting with different ranks based on these insights to achieve your desired outcomes in fine-tuning. This image provides a comparison of different optimizers for fine-tuning large language models. Each optimizer has unique characteristics that can significantly impact your training process. Starting with Atom W 8-bit, it's low in memory usage and offers fast performance, making it an excellent choice for Q-LoRa training, which is commonly used. The Atom W 32-bit variant, while also fast, demands higher memory, so it's better suited for full fine-tuning operations when you have at least 40 gigabytes of VRAM available. Next, we have SGD with Momentum, which is the fastest in terms of speed, but might require a slower start in terms of convergence. This makes it a solid option for continued pre-training tasks. The Lion optimizer is low in memory and fast, and it's considered experimental, sharing similarities with Atom W, which could be interesting to explore. Finally, Adafactor uses the least amount of memory, but features a moderate speed and convergence, making it ideal for setups with strict memory limitations. Understanding these differences is crucial as they allow you to choose the optimizer that best fits your specific hardware and training objectives. Next, take some time to evaluate which optimizer aligns best with your project needs before diving into the implementation. This image presents a comparison of batch sizes and gradient accumulation strategies for training machine learning models. It provides a clear breakdown of how the effective batch size is calculated based on the number of devices, the gradient accumulation steps, and the number of GPUs you have. You can see several configurations listed, detailing the values for per device, grad accum, and the resulting F batch. For instance, with one device and a gradient accumulation of 4, you achieve a small effective batch size of 4, which is the minimum safe configuration. As you scale up, such as using 2 devices with 4 accumulations, you get an effective batch of 8, which is a recommended starting point. The VRAM required increases accordingly, making it crucial to match your batch and accumulation settings with the capacity of your GPUs. The note on the sweet spot indicates that using 4 devices with 4 accumulations gives optimal performance on common GPUs. Understanding these configurations helps you effectively manage your resources and train models efficiently. Next, you should try adjusting these parameters in your training scripts to find the best setup for your specific tasks and hardware. This image illustrates the learning rate finder, a crucial tool for fine-tuning your model's performance. The graph showcases how the loss changes in relation to various learning rates, plotted on a logarithmic scale. Notice the curve where the loss decreases initially, but then starts to rise sharply. Your focus should be on the highlighted area, which indicates the optimal learning rate range. Specifically, you're looking for the best learning rate, roughly around 2E4, which is just before the loss reaches its minimum. Selecting a learning rate within this optimal range can significantly enhance your model's convergence speed and overall performance. Using this technique, you ensure that your model starts training effectively, avoiding issues like slow convergence or divergence caused by a learning rate that is too high or too low. So, take note of the best learning rate identified here, and in your next steps, implement this value in your training configuration. This is a foundational skill in model training that will serve you well as you continue to experiment and refine your approaches. This is a quick reference guide for configuring the training parameters in your LLM fine-tuning process. Each parameter is crucial for optimizing your model's performance while managing resources effectively. Starting with the per-device train batch size, it's set to 2 to conserve VRAM. If your system allows, you can increase this for potentially faster training. The gradient accumulation steps is set to 4, which helps compensate for the small batch size, allowing you to mimic a larger batch effect effectively. The learning rate of 2E4 is standard for LoRa. If you encounter instability, you might adjust this to 1E4. You've got num train epochs set to 3, which is a good starting point, but typically, you might find a range of 1 to 5 works best for different scenarios. The warm-up ratio is at 0.03 to provide a gentle increase in learning rate during the initial steps of training, which helps stabilize training. For dynamic learning, the LR scheduler type is set to cosine, ensuring a smooth decay of the learning rate. The BF16 parameter is true since it optimizes memory usage effectively on Ampere plus GPUs. Gradient checkpointing is also enabled, saving VRAM at a slight speed cost. The optim parameter is AtomW 8-bit, chosen for its memory efficiency. You'll log training progress every 10 steps, with checkpoints saved every 100 steps. Finally, max-sec/length is set to 2048, which defines the clip limit for your sequences. These configurations will contribute significantly to a successful fine-tuning process, so be sure to adjust them based on your specific requirements and monitor performance as you train your model.